Cool. Hey everyone, this is me. Thanks for I think I haven't been to any Bangalore meetup which doesn't mention traffic. So I know I'm in the right one, right? So thanks for coming down all the way from all the places. I've come from Pune all the way. So great to be here. I know you've probably had lunch and you like AC and it's all like nice cozy environment. Thanks Nasdaq for that. But I'll try to keep you awake by talking about interesting problems and challenges of scale that we have gone through. All right, cool. So this is the talk, which is around machine learning, scaling these workloads to like 2 million plus API requests to machine learning models, right, per day. A bit about me. I'm Chinmay. I go by Chinmay185 on Twitter, and I write I'm a founder at One2N, where I've worked on. We work with startups and scale-ups and enterprises to help them with reliability engineering and backend performance engineering in general. Right. I've uh, I write stories on pragmatic software engineer. I'm guessing some of you have seen those. How many of you are DevOps, SRE, platform, whatever the cloud, whatever is a term for it these days, right? Engineers. Okay, quite a few of you. How many of you are developers? Like, I don't deploy code on production. That's ugly. I write code. How many of you are developers? Okay, yeah. How many of you do everything? Awesome. Great. Great to see that. Um, Lastly, I love engineering. I'm a good like fan of psychology. I read a bunch of consumer psychology, that kind of stuff. I like percussion, so I play tabla, and I'm a big fan of this 25-year-old game called Age of Empires. If anyone, okay, you. Oh wow, not what I was expecting, but good to see you all. Next, yeah. So today's agenda is going to be like, what is ML ops? Uh, we've heard about this term called DevOps for I think since as beginning as 2011, 12, whatever. Right. So talking about what DevOps is, how does it relate to MLOps? And there is DevSecOps and there is DevSecFinOps, and then tomorrow, there'll be something more, right? Uh, and really, like I want to talk about some high-level theory points, etc., and then bring it back to production, right? Because that's very important. That what happens and how do we scale and deploy things on production. So that's what I'm going to cover as part of a real-world use case that we built. So MLOps is fundamentally, if you're okay, how many of you are data scientists or have worked with large data sets, or okay, I see a few hands. So MLOps is about making their job easier. Okay, fundamentally, it is about operationalizing or sort of data science part of it. So if you think about software engineering and DevOps, what these are, how these are related, right? I write code, I deploy this to production, right? So the whole deployment part of it is the operational part. Obviously, observability, running it on scale and whatnot. So this is where the DevOps cycle comes into place, and you kind of get a good feedback loop. And the idea is to have less silos, right? That's the idea. So same idea kind of applies to ML models, right? That's the underlying idea. How do we get these models to production, right? That's when the real value happens. So this is about that. And we'll talk about briefly about the phases. You build code, you then manage, like you have versioning artifacts, etc. Then you deploy and you monitor and scale and whatnot, right? So that's a various 4 stages that we'll talk about. So briefly, again, if you were to think same from software engineering terminology to DevOps or to MLOps, this is what it would roughly translate to. You'll have data extraction, analysis, blah, blah, blah. Basically getting the data ready for the model, right? Which is somewhat in some cases also goes into data engineering part of things. Then there is model training, model evaluation, model versioning, stuff like that, right? Which is around the whole data science part of it. Lastly, like at the end of it, hopefully you'll have some model that you think is going to perform well on production, which is where you try to now do the ops part, where you say, okay, I'm going to now figure out how do I deploy this? How do I monitor this? How do I scale this? How do I know the accuracy of the model? How do I do testing, right, of this model, whatnot? So ultimately, like it comes down to this feedback loop in like we have in DevOps, where you want to do continuous integration, continuous delivery, deployments, and there's one extra step with respect to ML models, which is the continuous testing part of it, right? Where you want to improve your model, right? Like we do with software code, you improve the code, you deploy, you fix some bugs, you introduce new bugs, stuff like that, right? So that's fundamentally, like, this is all sort of basic. uh, this is the only complex diagram I'll have, I guess. uh, Again, this is from sort of Google's ML guides, so you'll find that online. It's kind of talking about the same steps that we talked about in a more visual or more formal form, right? So again, you start with getting data. It can be offline data, it could also be real time data. Getting that is the challenge, so that's where the whole data engineering part of thing comes along, right? Then you have the whole, tuning the data, improving it and whatnot, and then the three steps of data model training and whatnot. Then you have, finally, hopefully, you have a trained model that you think is good enough, which you put it into the model registry, right? And then you're going to sort of deploy this and scale and run this. So today's talk will mainly be relevant for operational folks, where I'll cover point like 4 and 5 more. I'm not going to cover point 1, 2, and 3 in this diagram, which is around building the model, right? Which is where you've talked about some data scientist folks here. If you're interested, you should talk to them about that, right? So again, DevOps, if you just Google this term and look at images, this is the kind of image you will get. Although I've never kind of understood why they have this infinity symbol and who came up with it. I tried to do some Googling. Uh, I mean, the only logical sense that I could get out of is that there is a feedback loop, right? Which is what it's trying to indicate, that you don't do these activities one time. Like, you don't build the code, throw it over the wall, then operational people throw some things back at you, and then there is a tension between two of developers and operations, right? Which is what DevOps movement or practitioners or ideology is about, where minimizing these feedback loops, right? Which is where you have these dev and operations. So if we again were to think about ML in this way, right? How does it, where does it fit into? So again, you have similar, right? Data preparation you can consider as sort of coding, building, requirement, etc. Training is going to be again testing that part of it. Then you'll have model repository, which becomes your release artifact of some sort. Then you're going to model, like deploy the model, monitor the performance. And fundamentally, I think what is different for ML, which is kind of not that much applicable for application, is this feedback loop of continuous testing, right? That's what you would ideally want to do, because you're not going to get one model right at the first time. You're going to want to improve that. And how do you improve? Where do you improve? How do you test that the new model is better than what I've already deployed, and it improves in one factor but degrades in another factor? That's the critical part of it. In the simplest flow, like we saw in the previous diagram, it is linear, like it is manual, right? In terms of data extraction, etc. Idea, as you get mature in the whole deployment of these models, you would want to go through that loop often by doing automation of infrastructure, deployment, registry, etc. Right? All right. This is where the theory part kind of ends. I want to tell you like a story, right? So when I was in 10th standard, we had gone, like, my sort of schoolmates and I, we had gone to a different city for playing cricket, and we had a tournament and whatnot. So because it was a different city, we were staying at a different, like a hotel, where we did not know what it is like and how it will be, right? So we were in a hotel, placed in a hotel. Now what happened was, on the day of our tournament, there was some problem with the lock, like the door room lock. And I don't know how and why it happened, but it got jammed. So we were calling like reception 9, by dialing them and saying, okay, we can't open the door, something is wrong. Uh, they came in, they got the locksmith, they like took some time, and they finally like got us out in like 3 hours. By that time, our tournament was done. We couldn't participate, and we were like frustrated as to like, how could this happen? Like, this is so frustrating, right? Like, you got locked in a hotel room and you couldn't go to the tournament. uh, yeah, this was very frustrating. Except all of this that I just told is all made up. Like this did not happen. The reason I'm telling you this is, unfortunately, this is what I've seen. Like we don't play the game. We just don't go to prod. So many use cases that I have seen companies do, they want to have a perfect model, a perfect deployment, or a perfect data to be able to launch. And they never launch, right? What I'm trying to tell you here is, please, focus all of your energy as business to go to production and iterate, right? I think if we can only optimize one part in software development, I would say to optimize the feedback loop, right? Don't have a release cycle of like 6 months, 1 year. Like shorten that. Have faster releases. That forces you to have better automation and stuff like that. All right. So that is where what I'm going to talk about next, right? So we've had some production use case where we deployed the model to the scale that we talked about, and I want to talk you through the journey of how it happened, what all we did, etc. So this is a case study about a KYC kind of application, right? So a KYC means it's a know your customer. So you have some API, or you have some sort of like things like who you say you are. That's the idea, right? Like you go on to buy a new SIM card. People want to do your KYC, right? They'll ask you for Aadhaar number, PAN, or whatever, right? So it was a B2B application. So what the company that we were working with, what they did is they converted these into APIs, right? And this machine learning APIs needed to be scaled to the scale, like this 2 million per day scale, right? Uh, you might say, okay, what kind of like APIs are we talking about, or what are these? Like, make it concrete, right? So one was face matching. Given two images, check the similarity score of these two faces, right? So you would output something like a number between 0 and 1, for example. You want to have faceless, like face liveness detection. What does that mean? Like you don't want to have someone faking or spoofing by clicking a photo of a photo. You want to have a photo of a real person, right? So you want to kind of, even though we are looking at 2D photos, you want to figure out whether this person is real or it's a fake photo or whatever, right? That's another API, or that's another model that we had. Another model that we had was this, which is OCR. So imagine again, if you have a Aadhaar card or PAN card, I would click a photo, and whatever is written on the card, I'll get that information in some sort of text format, right? Uh, and more, there were some more kind of APIs, but for now, let's sort of focus on these, right? So this was the architecture overall, where we had the client SDK. Think of it as just the client, whether it's SDK or what, doesn't matter, where you're getting traffic um, to your API layer. And then what we do is we have these ML APIs which are deployed on the worker. So to be able to have sort of, we have some sort of a queue mechanism where we have RabbitMQ, where you would send some messages, the model, Python model or whatever, which is deployed as a service, would read that, return the response back to RabbitMQ, write something to database, etc. Right? So that's the kind of typical like 3-tier web app with a background worker kind of thing that you can think of. So here were our like goals or requirements, that we wanted to have like 2 nines of published availability. We wanted much more, but to be published as a SLO, we wanted 2 nines of availability, especially during the business period. We wanted to have like, obviously cost optimizations in terms of, we don't want to burn a lot of money for cloud providers, and less than 3 seconds of API latency for any of the model calls, or most of the model calls for 95th percentile, right? So that was like the goal, like that's what we want to achieve. So before we get to how did we achieve and what did we do, etc., I want to talk about a very interesting or important aspect that uh, I think is even more relevant these days, which is being cloud sort of agnostic. I think someone mentioned here that, oh, we were using some tool, but we didn't want to get locked into AWS, so we did something, right? So I think that's a point that is relevant even more these days. So what we had done was we built our system such that this can be deployed on any cloud. Like we could go to GCP, AWS, heck, we could also go on prem. Imagine if we had GPUs, etc. We would just deploy the same code, maybe configure a few things here and there, but the same code would be deployed there, right? That was the idea. So hence, like we had, image storage. We didn't purely depend on like S3 or GCS or particular cloud provider, but we had like Minayo, which is kind of open source tool distributed file system, which is S3 compatible, right? So if you use that, then underlying you can just switch any other object provider, object storage sort of service provider, and things should be okay, right? Similarly for Redis, we could go to self-hosted, and most clouds have a cloud offering like Elastic Cache in case of AWS, right? Or likes. Similar for RabbitMQ, again, it was some queue that we wanted to run and have it deployed. We could have gone to SQS or some other queue based on the cloud provider. And similarly for like ML workers were running on like bare GPUs. So assuming there is GPU available, they would run on EC2 or like even Docker or whatever, right? And Postgres was the database, so RDS or equivalent. So back then we were using Nomad as the orchestrator. Kubernetes was kind of not there because most of the other infrastructure was already managed using Nomad. And I think one of the other reason was because we wanted to do on-premise deployment, managing Kubernetes on-premise, we were not sure how comfortable the team would be, but we had managed Nomad on-premise ourselves. So we were pretty okay and comfortable with doing that. So that was the overall like tech stack. And sort of why cloud agnostic, right? Because we can package the same wine in different bottle, right? That's the idea. Like we could just take the same stack without any code change, just deploy it. So that gives us tremendous like flexibility and like almost zero vendor lock-in, right? So that's a very important thing, which is why I want to focus on this aspect. So in terms of scaling journey, it wasn't like, okay, we are running like getting few requests per day, and then boom, we get like 2 million the next day. I don't think many B2B traffic is like that. Maybe B2C could be one case, like if you go viral on social media. But typical B2B is like gradual journey, right? Where you know what you are getting into. Like you can slowly onboard new users, new traffic, which was the case in our case as well. So this meant we were live on production. We were optimizing for the iteration cycles, right? So for this, to be able to really think now from system design point of view to how do you get to achieve those SLAs or SLOs that I talked about, right? Uptime, latency, SLOs, etc. Idea is to eliminate single points of failure. You don't want to let your system go down because of some small issue with some system that you didn't think about. That is one. You would want to do capacity planning. If you want to have that much scale, you would need to ensure that you're able to predictively like add new nodes or scale system accordingly. You would want to obviously have some sort of auto scaling in place and ensure your costs are in check. You would have to do all the other DevOps kind of related automation, which is deployments, like observability, bunch of things around that, right? So, and what I'm going to also discuss today is like two production incidents that we got, and that taught me a lot as an engineer. So, to make it more concrete, right? So, let's talk about the first point, eliminating like single points of failure. So, it's the same architecture here. We went about checking, okay, what if we need to have high availability for almost all the components, right? So, we need to have RabbitMQ as high availability because that's like the main critical path. So we would have to have queue replication, cross AZ deployment for the nodes, and maybe worst case, if we couldn't manage it ourselves, go with something like cloud managed SQS or whatever, right? Similarly, even for ML workloads, back then we were on one cloud provider, one region. We wanted to make sure our nodes are deployed across AZ. So that means we had to fix our deployment automation, fix our auto scaling such that new nodes are not only scaled in one zone, but they are equally scaled in like both the zones. So almost like a odd even kind of parking that we have, right? Like you park here one day, you park on the other side of the road next day. So you want to have deployments such that it can deploy on both AZs, right? And still manage the auto scaling accordingly. Uh, we could also use SaaS offering for some other components that we didn't want to manage and take overhead of. The idea here is stateless services or stateless component are much easier to manage than stateful ones, right? Where we have to think about storage, backup, reliability, way more harder in case of stateful components. So for capacity planning, again, we've talked about single point of failure, talk about capacity planning, right? So for capacity planning, idea is where is the bottleneck, right? Like, because the strength of the chain is the strength of the weakest link in the chain, right? That's the idea. So you want to find out the bottleneck, you want to make sure you can scale and manage that, and then find out to the next bottleneck and do the same thing, right? So we looked at, okay, can API be the bottleneck? Will it be DB? Will it be workers? Stuff like that. Turned out, or like sort of guessable at this point, that workers, ML workers usually are like the slowest and most costly. So look at those. So then this begs the question, how many workers or how many jobs can each machine take, or how many ML model requests per hour, per minute, per unit of time I can get out of a single node, right? If I have that kind of concurrency and background saying, okay, look, there is this configuration of a machine which can handle like 5,000 requests per minute, concurrent requests, or total 5,000 throughput is 5,000. And if I'm getting XYZ traffic, then we could apply some sort of mathematical laws, like there's a law called Little's law, universal scalability law, like some napkin math we could do, and we could get those numbers. So which is what we did. By the way, again, there is this, if you're just interested in this particular part of thing, I've got a talk that I did earlier. It's on our one-to-one like website channel, YouTube channel. So you can take a look at that. Again, this is around how do you optimize application performance from first principles, like how do you think about it, right? Totally. So 1 to n, just search for 1 to n on YouTube, you should get hopefully the first thing. So cost optimization, auto scaling, people who have run GPUs on production would relate uh, to this, and this was very critical, important for us. So to solve that, we were again like, let's think, what is the metric we can auto scale on, right? Like, can it be CPU or GPU utilization? Do you get that number somehow? Can you trust it? Is it memory? Is it queue depth, like the number of requests? How do we know? So again, you do some sort of load testing, and we kind of went into a combination of these, which I'll cover in the next slide. Somewhat combination of these, right? So this is what finally we ended up with as an autoscaler. Again, remember, this was on Nomad, not on Kubernetes. I think if I were to do this today, I could probably use HPA, GADA, stuff like that to be able to do this much more easily today, right? And I'll not go through this slide, but you kind of just take a look at the left side, the green part, which is you get some idea of what's the current traffic that you're getting, what's the current number of nodes that you have. And because you know the unit economics, you know that, hey, one node can handle this much, and I'm getting new traffic at this rate. I can write some basic linear regression or whatever logic to come up with how many desired nodes I should have. Again, you have to take into account the lead time to provision a node, because like the machine learning nodes, to be able to come up and for the Docker container to serve, it takes time, because typically the Docker image size would be like in GBs, right? It won't be your typical Go node application with less than 500 image size, right? It will be much more in our case, it was probably 7 or 8 GB as a model size. So to be able to pull that Docker image on a node, run that, get the service up and running, takes like 10 minutes. So you have to accommodate that time as well when you scale up, and similarly for scale down. So anyway, and we wanted manual overrides and whatnot, which is where some custom autoscaler back then. Yeah. Yes, I'll get to that. Yeah, that's an interesting point. So there is this again. If you're interested in this, there is a case study on our like website. If you just go one2n.in, you will find the case study over there about machine learning model scaling. Right. So I want to talk about two issues on production that we faced and how we dealt with it. So one was you just mentioned, can you run multiple GPUs? So we had this, right? Like imagine a GPU machine that you get from a cloud provider. It has got the GPU, it's got its GPU memory and cache or whatever, right? When we were running, because we were using Nomad and we were using the raw Docker driver, whatever is the default Docker driver, we would see that we can only deploy one Docker container on a machine, right? And with that, if we just try to look at the utilization, etc., we would probably see 20% utilization. So the next question is, why can't we deploy more, right? By default, there is an open issue in Nomad where you can't really deploy multiple Docker images or Docker containers on a single node with GPU. So how did we get around that? We said, okay, let's use a exec driver, raw exec driver. So the raw exec driver in Nomad, what it does is it allows you to say, you don't worry about what workload I'm running. I'll worry about that. And that means it just asks you to like the format there is, you run some shell script essentially, or you run some command, right? And we use raw exec, which means we actually ran our own Docker Compose. So Nomad was scheduling Docker Compose. Docker Compose was running 3 or 4 containers that we wanted, and that way we could optimally utilize the GPU. And that brought down our cost like 4x, literally. Like, yeah, so I think we haven't checked Kubernetes, etc. But today, if I were to do it, probably I would use a much more mature tool like Kubernetes. I think it's much more mature these days. But this was a problem that we have had to solve, because without which we would straight away have 4x cost. So if we would need $10,000, we would have to actually pay $40,000 per month, which was just massive difference. So this is the issue that I was talking about. As of today, I just checked again; it is still open. And again, the workaround that I had proposed back then, what we were using, that's pretty much is what most people are using right now also. So that's just how state of the things are right now. Uh, so the second production issue that we got was again super interesting. This is kind of way more interesting in terms of debugging. I've actually also written a story about this on Twitter. I can link it later. But the idea or the problem here was, suddenly when we wake up the next day, things are like running fine on production for months, right? And we start seeing, when we onboard new customers now, we start seeing API latency increase. Like it goes to 25 seconds or more. Remember, our SLA was what, 3 seconds, less than 3 seconds for 95th percentile. This is way crazy, right? So we're like, okay, what's going on? Like, we get an alert, we go and fix it. We try to check where things are going, what's going on. First thing, the culprit comes to mind is the ML workers, because that's the slowest part, right? We have established that that is the weakest link in the chain. Let's look at that. There is no queue depth. Queue depth in RabbitMQ or any queue mechanism means, are there any pending jobs to be processed? No pending jobs. Okay, so, well, that's not a problem. Then why? Like, where is the problem? So in the worker machines itself, can we go log in and check or whatever if there's some problem there? There is no processing lag. The latencies on that machine, if you go on a particular machine, just do some hacky tail of logs and whatnot, we find it's all running normal. Where is the problem? Why is there a problem? So long story short, like, you can read the Twitter thread later, but what we realized then is that the number of Go routines, again, this was written in Go, the number of Go routines that would consume the message from RabbitMQ, right? Remember the request flow? You would get APIs sending data messages to RabbitMQ. RabbitMQ would, like, your workers would process that. They would send the result back to RabbitMQ, which API is going to listen to. So there are some workers which are running on API to process results from RabbitMQ, right? And we had not auto-scaled workers or the API that much, because Go binary is pretty small. It was able to handle traffic, no problem. But suddenly, as somehow traffic increased, the API nodes, there was no CPU utilization or whatever, but we had this problem that there were only 5 go routines that were running, which was consuming the from the RabbitMQ. So we increased that to 30, and that problem got solved. So immediately then we get like reduced latencies. So that, like, I learned something that day, that if you go with a preconceived notion, because that there is going to be a problem with this component, and you try to focus all of your attention on that component, typically in our case the problem was somewhere else. So we went with a preconceived notion, try to look for problem there. We didn't find it. We spent like hours, couple of hours. Why is there no problem? Like, we were just fixated so much on RabbitMQ and workers that we miss completely something which is super obvious if we were just we were to take a step back, right? Yeah, yeah. So now this is so what I want to. So, yeah, the good question, right? So we had no queue depth, but again, here I'm oversimplifying a bit. There were couple of queues. One which was where the worker was reading the messages, right? And the other queue is where worker is pushing the messages onto the queue, where API is the consumer. We never looked at that API consumer queue. We were like, no, there cannot ever be a problem there, because in all of our load testing, in all of our past operations, we've never had a problem there. So we were completely oblivious. And later, when we looked at, like, we had a filter in RabbitMQ monitoring to only look at the worker queues, and that's where we didn't even look at the other queues. Yeah, API was not consuming. So essentially, worker was doing all of the job. It was also sending data back to API, but API workers, there were just too few, and they were running behind. And that's completely. Yeah. So I think the question for everybody is, didn't you have observability to give you this metric in some way? So the answer is kind of yes and no. Yes, we had the observability, but we were so focused on looking at one problem, that is where it was just not it was a problem. Later, yeah, we added more kind of end-to-end latency, and we added some sort of tracing, hacky tracing way, because again, we wanted to fix something real quick. So that then gave us this observability that, yeah, where we need to check where the actual latency is coming from in some way, right? So okay, this was again sort of interesting issue. People who have deployed, worked on production, they'll know when the incident happened, the thrill and the challenge. Like, you get so tunnel vision sometimes that you don't take a step back, right? And people are asking you questions. Hey, why is it still not fixed? Why are we like having complaints from customers, right? So you don't have time to really think calmly, right? So that's something that I learned that day, that yeah, like, you need to really take a step back and think well. Cool. I think that's it sort of from me. What you can connect me with, on Twitter, LinkedIn, etc. Check out these stories that I talked about. They're on the playbook.